We now see one use for the dot product, and that is a way to find the angle between two vectors. I encourage you to please look at page 745 in your textbook for the proof of why this works. It's very, very interesting. And if you haven't already figured it out, your math textbook is the single best one you've probably ever seen. I know it's the best one I've ever seen. It has great explanations, and if you are in the e-text, you could look at the videos. I like the hard copy myself, but it's nice to know that those videos are available in the ebook to supplement these with. So here's how you find the angle between two vectors using the dot product. The cosine of the angle between the two vectors will be equal to the dot product of the two vectors divided by the product of their magnitudes. So there's the magnitude of V and there's the magnitude of W. So in other words, theta itself, the angle between the two vectors, will be equal to the inverse cosine of V dot W divided by the magnitude of V times the magnitude of W. So in example 2 we have here, find the angle between vector V, which is -4, 3, and vector W, which is -6, -2. Round to the nearest tenth of the degree. Alright, so the angle will be equal to, we might as well just go ahead and use this part of the formula since theta is what we're interested in, the inverse cosine of V dot W. Okay, so remember the dot product is the horizontal components multiplied together plus the vertical components multiplied together, divided by the product of the magnitudes. So the magnitude of V would be the square root of -4 squared plus 3 squared times, now not dot, times the magnitude of the other vector, vector W, -6 squared plus -2 squared. Okay. So theta is equal to the inverse cosine of, that's 24 plus -6, which is going to be 18, divided by, that's 16 plus 9 is 25, square root of 25 is 5. 36 plus 4 is 40. It doesn't have a square root. We might as well just leave it square root of 40. And then we turn to our calculator and we find the angle between the two vectors is 55.3 degrees. I want to verify that on GeoGebra just because it's rather fun. So we had one vector was -4, 3. So I'm going to go -1, 2, 3, 4, 1, 2, 3. The other vector was -6, -2. So 1, 2, 3, 4, 5, 6. -2, bring it down. I'm off the page a little bit, but I can see there that that's the correct vector. And look, the angle between them is 55.3 degrees. So it's nice to see that as well. All right, let's take a look at another example here. We have find the angle between -4, -1 and -2, 8. So theta will be equal to the inverse cosine of, numerator will be the dot product, -4 times -2 plus -1 times 8 over, hold on a second, -4 times 2 is 8, -1 times 8 is -8. That tells me the numerator is going to be 0. Then it doesn't matter what the denominator is. We know it's not 0 because it's magnitudes, and magnitudes are lengths. These are not the 0 vectors. 0 divided by anything is 0. So theta is equal to the inverse cosine of 0. Well, I don't need my calculator to tell me what theta is. That's a unit circle angle, and it is 90 degrees. So these two vectors form a right angle. Let's see if we can see that on GeoGebra. So here we see them graphed on GeoGebra, and sure enough, dot product is 0, and we have a right angle shown here. So this is something that we may want to remember. If the dot product is equal to 0, that means the vectors are perpendicular. Well, we're going to learn a new word for perpendicular when it comes to vectors. Vectors that are perpendicular are referred to as orthogonal. So I'd love it if you said that word out loud right now wherever you are. Orthogonal. It's another one of those that just fills up your mouth when you say it. Orthogonal vectors are perpendicular vectors, and that's going to happen whenever your dot product is 0. Your book doesn't talk about parallel vectors, but I think it would be important to just mention it because you may see it from time to time. If your result comes out to be 1, now not your dot product is 1, but if theta is equal to the inverse cosine of 1. So you work out the dot product divided by the product of the magnitudes and you get 1. Think about what that would mean. Okay, what has a cosine of 1? Well, that would be 0 degrees. That means there's 0 degrees between the two angles. Between the two vectors, I should say. That indicates that the vectors are parallel. You won't see that a whole lot in this course, but you could see it in other places, so I want to mention it. But I do want to stress, all that mattered was that the numerator was 0, because 0 divided by anything is going to be 0. So when you have a dot product of 0, we know the vectors are going to be orthogonal. But we've got to do the whole computation, dot product divided by product of the magnitudes. If that comes out to be 1, then we know our vectors are parallel. So one more for practice. Find the angle between V and W. So we know theta is equal to the inverse cosine of. Let's see if we can go ahead and do the dot product and not multiply the whole thing out. 5 times negative 5 is negative 25. Negative 1 times 12 is negative 12. Could we go ahead and do the magnitudes in our head as well? That's going to be 25 plus 1, that's square root of 26, times negative 5 squared is 25, 12 squared is 144, 25 plus 144 is 169, square root of 169 is 13. So on our calculators, and I mean you could let your calculator do the whole thing, of course, that's not a problem. We'd have negative 37 divided by 13 times the square root of 26. Before we do this calculation, let's see if we can predict whether the angle will be less than 90 or more than 90, somewhere between 90 and 180, because it wouldn't be more than that. So let's see. The cosine has a negative numerator, positive denominator, so that means the cosine is negative. Well, that means we must be in quadrant 2, where angles are between 90 and 180. So we're expecting an obtuse angle as our result. So when we do the inverse cosine of this, we get 123.9 degrees, solidly in quadrant 2, just like we predicted.